And our last talk for this morning's session is by Payne from Nuclei. Will be telling us about assessing 14K roles. Okay, take it away.
Great, thank you. So hi everyone, I'm really excited to be here today to talk about my work on assessing 14KO, which I have nicknamed the Extragalactic Old Faithful because it undergoes periodic flares in the X-ray, UV, and optical, which we think could be a repeating partial TBE. So if I were to sum up kind of the story of this object, it would be that you don't know what you'll find when you're sifting through a large amount of data, but also if you find an oddball, it can always surprise you and get even weirder. So I developed a large sample of highly variable AGN observed by the Assassin survey, a very small subset of which I'm showing here. And as I was going through the sample, I came across a light curve that immediately stood out, as opposed to the expected stochastic variation we see as the hallmark of AGN variability. There are evenly spaced flares that rise well above the quiescent level. And we detect these flares over the entire duration of the Assassin light curve for this object. So since it started observing this object since 2014. And there are missing flares, so to speak, due only to seasonal gaps in the light curve. I know here I'm showing separate V-band and G-band. So when Assassin first started its survey, we were observing in the V-band before switching over to G-band in 2017 to achieve a fainter limiting magnitude. And I've been referring to this object as Assassin 14KO because one of these early flares was detected by Assassin. It was assigned the name 14KO and reported as a new transient. But it was a case of a mistaken identity. At that time, there was a follow-up spectrum taken. There was a blue continuum and hydrogen emission lines. So it was tentatively classified as a core collapse supernova, but very close to the nucleus because this is very clearly a nuclear transient. But it was also acknowledged that, again, this was within a known AGN. So it was stated that, it could possibly be an AGN flare. It's definitely not any type of explosive transient, such as supernova, because these flares kept happening. But now we have more than 24 individual flaring events observed by Assassin, so we can start to characterize and understand its periodicity. So measuring the peak timings for each individual flare and comparing that to the calculated or expected time, just assuming a constant period, there are very clearly residuals in O minus C or observed minus calculated parameter space. And the presence of these residuals indicates a period derivative. So fitting all of the O minus C peak timings, we find a mean period of about 115 days, and also a negative period derivative on the order of 10 to the minus 3. So over time, the mean period is getting shorter. And if we, and also, the fact that the mean period is 150 days, it's kind of this intermediary. It's definitely orders of magnitude larger than what we see with QPEs, which are hour-long timescales versus other previously studied well-known objects such as OJ287, which is on 11-year timescales. So this is a nice human-friendly 100-day period. And if we phase fold the Assassin data according to this period model, it's very clear how very consistent the flares evolve over these long timescales. There's always a very rapid rise to a singular peak, followed by a more gradual decline. And these events are still fairly rapid. They're only lasting about 50 days each. And as I mentioned before, this object is within a known AGN. Its host galaxy is ESO 253G003. And this object has long been known to be an AGN. It was first classified as a type 2 Seifert back in the 80s and 90s. It was also noted in these catalogs that this is definitely a late stage merger system. There's a very noticeable kiloparsec scale tidal tail. This picture came into clearer focus a few decades later with high resolution infrared imaging, which showed that there is a bright central source, but to the south of that, there's also this fainter secondary source as well. And these two sources are separated by 1.4 kiloparsecs. This picture came into clearer focus with archival Muse IFU observations, which showed that both of these sources are consistent with being AGN, according to standard VPT diagnostics. And these two sources are quite distinct spectroscopically. The northern source is characterized by very broad, prominent emission lines, whereas the southern source only has narrow lines. So the question immediately becomes, okay, well, we know there are two AGN, like which is causing these periodic flares? And thankfully, Pan-STARRS helped us answer this question. So Pan-STARRS has the necessary spatial resolution to resolve out the two sources, and also during Pan-STARRS normal survey operations observed this object many times during times of both flaring and during times of quiescence. So through difference imaging, I was able to very clearly see that only the brighter northern source is the one that's brightening during times of flaring event. There is no change in brightness at all from the southern source. So we can definitively say the northern source is the source of assassin 14KO. And because we know that they're separated by 1.4 kiloparsecs. That's much larger than the light travel time for between these two sources compared to the period. So there's no influence on the southern source compared to the northern source. So, okay, we know that the northern source is 14KO. So now we can take a closer look at the spectra. And as I mentioned before, it's characterized by these very prominent broad lines. And specifically, the lines are double peaked. And whenever we see a double peak structure, we think this could be a relativistic accretion disk around the black hole. So we applied some different disk models. Right off the bat, a circular disk model was not able to reproduce the line profile for H beta very well. It does produce a double peak structure, but there's this asymmetry that it's not able to reproduce. On the other hand, elliptical models and a circular disk with a spiral arm was able to reproduce the asymmetries very well, shown here. And they're very similar, so it's a bit difficult to distinguish between them, but what we can distinguish between them is characteristic variability timescales. So for an elliptical disk, there's a precession timescale, and the best fit for this corresponds to a 70 to 700 years, which is very different compared to the spiral model, which has a dynamical timescale, and the best fit for this model is a dynamical timescale of about 140 days, which is remarkably similar to the period that we get from the light curve. Another thing to kind of think about for thinking about a spiral arm is, in the case of a TDE, we'd expect the debris to interact with the disk, producing a spiral arm, possibly that propagates through. So in general, it seems like this spiral arm is something to kind of keep in mind for this object.
Sorry, Anna, you say it's a good fit, but my eye, so it doesn't look like a good fit. I'm confused. What do you mean by a good fit?
Right, so this is all very qualitative. So I'm comparing this red line, and also we're not fitting the narrow lines. We're only fitting the broad line. So I'm just comparing the red line to the broad feature, which is the data.
Oh, so that one, the residual is a narrow line?
Yes, the residual is showing the narrow line because we're not fitting the narrow line at all, only the broad line.
Even the narrow lines look a little bit like they're broader towards the blue end. Is that common to see? Or?
Yeah, that's a good point. Again, these are very complicated line profiles, and definitely this is definitely kind of a first step into thinking about it more. But yeah, that's absolutely, I agree with that. So we're in a really unique position, right? We know pretty well when future flares are going to happen. So for the past several years, I've been requesting Swift TROs to understand the higher energy connection in addition to the optical. And Swift revealed very clearly there's a strong and consistent UV optical connection. Over all UV filters, it tracks very well with what we see in the optical. There's a rapid rise to a singular peak, followed by a more gradual decline. This is very consistent for each flare we have, Swift out of 4. It's also very well fit by a black body. And again, comparing individual flaring events, the black body evolution has been very consistent between them. There's always a consistent temperature range between 10 to the 4.2 to the 4.6. But by far, the most detailed look we have of these flares comes from the test data. So we got very lucky because TESS was viewed one complete flare fairly early on in the mission too, during sectors 3 to 5. So the way TESS works is it stares at a patch of sky for one sector, which corresponds to about 30 days, before moving on to the next patch of sky. So TESS was pointed at just the right time, at just the right location to capture one flare evolution. We also got lucky because later on in TESS's extended mission, 2 years later in 2020, it again was pointed just right for us to capture another flare. Note here that the scatter is much larger because in TESS's extended mission, they increased the cadence from 30 minutes to 10 minutes, hence why the scatter is larger here. But regardless, we're in a really unique position because we can now compare in a very detailed look 2 different flares 2 years apart. And that showed that there were, the general trend is still the same. We're seeing a rapid rise. It happens about 5 days, followed by a more gradual decline. But we are starting to see some small variations. In 2020, that flare rose, took about a day longer to rise to a fainter peak, and there was a bit of a more shallower decline. So again, same general shape, slight differences. But what was really important from the test data is that we conclusively see just how smooth the evolution is, which was definitely not apparent at all from the ground-based data alone. And we really relied on TESS's really exquisite photometric precision and extremely ultra-high cadence. And the fact that we're seeing a very smooth evolution is very un-AGN-like. We would expect to see, if it was an AGN or more heavily influenced by the AGN, we would see small bumps and wiggles superimposed on top of the flare itself. And we also see, and Subi kind of mentioned this in the talk this morning, we also kind of see this smooth evolution with test data in other objects. So Assassin 19BT was the very first TDE observed by TESS. And again, we see the smooth variation. There's no small scale variability superimposed on top of the flare. But this really drives home the point of these different timescales. So what we see a lot with TDEs is they happen over hundreds of days, which contrasts very sharply with what we see for 14KO, where each flare lasts about like 40 to 50 days. But what was interesting is if we just arbitrarily shrink down 19BT onto the scale of 14KO, the shapes of the profiles are eerily similar. But again, the timescales are very different. If we take a look at the rise times, 19BT, along with some other TDEs, all appear to have a T-squared rise, which we expect to see for just a very simple outflow at a constant temperature and constant velocity. That's very different what we see with 14KO. We actually see more of a linear rise. So is this something to do with different systems? Whether, and again, 19BT was a one-time event, so possibly a total TDE. So is this difference, could a difference in rise times possibly indicate partial versus total? It remains to be seen, but just something to keep in mind. So far, I've been talking about the UV optical because we see a coherent picture, but now I would like to move on to the X-rays. And we see something completely different in the X-rays than what we see in the UV and the optical. So as opposed to the singular brightening event, we see the X-rays dim. And this X-ray dimming happens at the same time. It starts pretty much at the UV rise and then through to the UV peak. And I've been monitoring the X-rays for the past several years using the the Swift TOs, but also through a NICER Cycle 3 GEO program. I've been getting X-rays during times of flaring events, but also during quiescence. And thankfully with NICER, we see something that we didn't know with Swift, and it seems that the X-rays gradually brighten in between the flares. But again, during the flares, there is a singular prominent dip in the X-rays, but there's also possibly a secondary dip that happens during the UV decline, although the scatter is a bit larger here, so a bit difficult to tell, but it appears to be a common feature. And the X-ray minimums are definitely not consistent. We're seeing a range of X-ray minimums that have been happening over the past few flares. There's also a trend in the hardness ratio. So we're consistently seeing that the X-rays are harder when fainter and softer when brighter. However, the column density did not change. So this would rule out the possibility that the change we're seeing is due to change in absorption. But as is extremely apparent in this plot, the error bars are very large, which would call into question this. But thankfully, we have another data set to kind of support this. And that's with Chandra spectra. So I obtained 2 Chandra spectra through DDT. These were taken during the December 2020 flare, which also showed no change in the column density. And the Chandra structure are pretty important here because Chandra can separate out the 2 sources, which is extremely important because we know that there are 2 AGN in the system. The Chandra data also showed that the northern nucleus, which again is 14KO, overall is dominated by softer X-rays, whereas the southern source is definitely more dominated by harder X-rays. And we also just did here, another object that undergoes extreme X-ray dip from atom, but also I wanted to point out that there is another object, Assassin 18EL, which was also showed kind of a similar type of X-ray dimming with a lot of differences, however. So again, with this object, there was a prominent UV optical brightening that corresponded to an X-ray dimming. The X-ray dimming happened during the UV decline, however, so there are a lot of differences between 14KO and 18EL. The big difference is, again, the time scales. This happened on hundreds of days versus 50 days. Another big difference is the hardness ratios. So for 18EL, during this X-ray dimming, it became softer as opposed to harder. But in general, we're adding to another kind of pool of objects that are undergoing these X-ray dimmings. One proposed model for 18EL was a TDE that came in, disrupted the disk, it initiated an intense period of accretion, but then depleted the inner part of the disk. and destroy the X-ray corona, hence the softening of the X-rays and the X-ray flux dimming. So this is one potential model that was applied to this particular system. So we're kind of building this multi-wavelength picture if we kind of zoom out a little bit. To summarize, the UV optical behavior consistently shows a sharp single rise and a smoother decline. This is very different from the X-rays, which show luminosity decrease. And for the X-rays, whenever the X-rays are fainter, they get harder, but they're brighter and softer. So I've been talking a lot about photometry so far, so I'm going to move a bit into spectra now. And so again, kind of keeping with the theme of this object, it shows very rapid, dramatic changes over very short timescales. So through HST cycle 28, I obtained 4 epochs of UV spectra. This first was in the December 2020 flare, and these spectra really surprised us. So the very first epoch we got was this blue one taken at -4 days relative to peak, so very early on in the UV rise. And it showed over several lines, very broad absorption features on the blueward side of the rest frame wavelength of different lines. It's very dramatically seen in the carbon-4 line, and it's very easy to see if we kind of isolate these individual lines. So during the UV rise, we see this 2-component absorption feature, but that's also seen in silicon-4. But that absorption feature immediately goes away 4 days later, and the spectra in general are dominated by emission during the UV declining phase. So this absorption feature kind of, then we were wondering like, okay, so when can we constrain better when this actually starts? I resubmitted another HSC proposal to obtain even earlier spectra to try to see, the correlation between the UV lines and the X-rays. Those correspond to the -9 days and the -12 days. However, these 2 epochs are identical to the quiescent spectrum taken at -36 days. So I was able to time it very well. It was taken during the this one first. It was taken during a X-ray minimum. So we were able to predict it nicely to target that time range. But one possible reason and difference between these 2 interval flares is that the X-ray minimum was not as dim compared to when the broad lines form. So it's just something that, we're acknowledging. Whether it's connected or not remains to be seen. But in general, we're seeing that, at -9 days, -12 days during the X-ray minimum of this one particular event did not show any strong absorption features. So we're now kind of, we want to zoom out and try to understand all of these different data sets and to try to form a cohesive picture. But it's been very challenging. So the UV spectra, the line widths that we get are about 5,000 kilometers per second, which I have lines here that correspond to circular velocities to guide the eye. So the UV spectra live up here at about 5,000 kilometers per second, which is several orders of magnitude larger compared to the black body radii we get from the SWIFT data. So it's difficult to place the scales of these different data onto one cohesive picture. So that's work that needs to be done. But again, kind of the $1 million question is trying to figure out what exactly this weird object is And as I mentioned at the very beginning, one possible scenario is that this is a repeating partial TDE. So in this view, each pericentric passage corresponds to one individual flare, and the orbit is about 115 days, corresponding to the mean period. This would have to be a very evolved star with a massive core and a puffy extended envelope, because we know that these flares are very long-lived. They've been happening since at least 2014, but again, that's only because we have assassin data since then. And we don't really have any way of, I've looked in earlier data, such as with the Catalina Sky Survey, not able to find anything due to the quality of the data, but clearly these are very long-lived. And a star with a massive core and a puffy envelope would enable this to be happening for a very long time. So if I were to kind of make a list of, a summary of why we think this could be the most likely scenario, looking very simply, putting a star on an orbit is a very strongly periodic signature. And looking at the peak luminosity over the duration of the flare, we get about 10 to the -3 solar masses, mass loss for each flare, which again would support thinking that this is a very long-lived event. We also see very strong UV optical evolution, which we do see for many other TDEs, and there's clearly a connection with the X-rays, and there are many open questions with that, but there's clearly, a connection between the X-rays, UV, and optical. Also, something that we really have to keep in mind is seeing the smooth evolution in tests. There's no small scale variability, and comparing test light curves for other TDEs, they're quite similar. Also, we know from, the host galaxy that it's a post-merger system, which have increased TDE rates. And there have been some recent papers that have taken an analytical look at 14KO, which also kind of support this partial TDE scenario. In Liu 2022, they found that the timescales will be drastically reduced by just putting the star on an elliptical orbit, kind of what we have been just talking about. Also in Q4 2022, they looked at this problem and said that they invoked the Hills mechanism, and they said it is possible to put a star on specifically a 150-day orbit to enable repeated partial TDEs. And also when we were first thinking about different scenarios, we also kind of thought about it being a supermassive black hole binary system, which also would cause periodic events. But this seems unlikely based on the measured period derivative, because it's an order of magnitude larger than what we expect if it was a black hole binary system. But there are lots of caveats with the system. Yeah.
When you say that, you mean if it was just disrupt, you get a repeated TDE around one of them, or are you saying that if you got?
Oh, so instead of it being TDE, if it was just a black hole binary system.
Oh, okay. You
Yeah.
both agree. Got it. Sorry.
But again, there's still a lot of work to be done with the system, and there's many caveats. In Brian's paper, if we interpret it as an emery, it's able to get a period of about 100 days, which is very similar to our observed period, and definitely would be observable based on the short destruction time. And there are lots of other questions that I would love to discuss, forming one cohesive picture, considering all of the observational data, the scaling issues I just talked about, not issues, but just differences, and also thinking about how the X-ray dimming fits into the UV optical brightening. And also, I also have to say that this is a very messy system. We know that this is an AGN, and AGN are also extremely complex. So how do you parse between two extremely complex objects? It's just a really difficult question. All week, we've been kind of also thinking forward and thinking about how we find other objects. I just want to very quickly advertised that, with Assassin, we have a new, as of this year, new Sky Patrol version, Sky Patrol version 2. So as opposed to previous years, all photometry for objects is being continuously updated on daily timescales. So it's a lot faster to get a lot of light curves very quickly. This is done through the online web server, but also new this year, there's a Python client. So you're able to get lots and lots of light curves extremely quickly, updated every day as well. So as I said at the very, very beginning, this object is weird, but also it continues to surprise us. So very new this year, in the past 2 flares in January and May, we're seeing a brand new behavior. So we've always seen it brighten one time to go to a singular peak, but it is clearly evolving. We're now seeing a double peak in the light curve. So this is, again, really new. I'm about to submit a paper on this new behavior, but something to consider and see what happened, see what happened in the future.
What's the time difference between the 2 peaks you're now seeing?
It is about 20 days.
Which is comparable to the duration of the flares themselves.
Well, also very weirdly, it's kind of it's kind of becoming a longer event too. So not only is it kind of showing this double peak, but it started to last a bit longer. So more about like 60 days. Unfortunately, the reason that the most recent one cut off is because we're now in another seasonal gap as well. So it's behind the sun, so we can't observe it yet. But definitely the next flare happens August 20th is the predicted flare peak. So have to see then what happens.
Do you have any X-ray data during these most recent flares?
I do, and that is ongoing work.
That one flare, like sort of before the weird behavior started, seems like much bigger than the rest. Do you see those like bigger flares than the previous years have done it too?
No, yeah, so if you're talking about this, yeah, so that is the brightest it had ever been. So that is another kind of anomaly. This happened last year in 2022. So that, could that have been the trigger? Was there this massive accretion event that triggered something? Yeah, but that is the brightest flare it had ever been that we have data for.
And otherwise, it's like the peaks are like fairly stable.
The peaks were fairly stable, yeah. I think that's most apparent in kind of the phase folded light curve.
Does the peak reach like the Eddington limit for the black hole, or is it nowhere close?
No, this is definitely sub-Eddington. It's way below. It's like less than 1%.
Okay.
Let's maybe thank Anna and then. Yeah, some questions. Jay.
So if we go back one more slide, is there an increasing trend, overall increasing trend over the last several years? From 2020 to 2023, I see like it's going up.
Yeah, that's another thing. So yeah, we do kind of see a brightening in the continuum. So that is another overall trend that we are now seeing that wasn't really super apparent before.
In the continuum, not between, sorry, when in the luminosity between flares or of the actual peaks. I thought you'd show that the peak luminosity is declining a bit.
Right. So so that's is kind of the overall kind of level. So it's on top of, so with the level on top of the flare itself, it kind of is like trending up.
Okay, that makes sense.
That could just be the AGN activity, right?
Could be, yeah, maybe.
I mean, if you're slowly, if it is a series of partial disruptions, you are slowly increasing the mass in that disk. And so if you're just kind of dumping on a little bit each time and that's producing the flares, it kind of circularizes. You also have like a larger, in principle, disk of materials that seems potentially consistent.
So one of the test flares had a precursor. Is that real? If you go back.
You said the tests?
Yeah, one of the test light curves. When you're comparing with 19 BT.
One second. So are you talking about like the continuum
Yeah,
level?
maybe one more plot down, next slide. Maybe one more. If you can scroll through, I'll let you know. There, yeah, you see that red curve, there's a precursor.
Yeah, so, but the question is that related to it, or is that just AGN variability? I think it's kind of hard to, it could be, yeah, maybe it is. But we don't really see that in Assassin. Again, it's ground-based, so it's hard to tell, but I did look at quiescent level and there's not really any clear, consistent behavior before.
One thing that I think, oh, sorry. There you go, you got, I already talked. Okay, I think one thing that's potentially constraining is if this was from the Hills mechanism from a stellar binary, and this kind of touches on what Mike was saying earlier, it's actually incredibly constraining on the properties of the binary. You'd have to have them like in separations of like, I think the Pufari paper mentions this, of like of order of solar radius. And so you first of all have to probably have one of them be a more compact object. And second of all, you wouldn't necessarily be able to have a larger mass or more evolved star unless it's already interacting. Interesting. So if it is from that mechanism, there might be, especially because you're continuing to see this for a while, and I think the total integrated mass might still be below one solar mass, but it's probably getting close to that limit. And so it'd be, you could say, oh, either you need a full disruption varies, you need it to like be overproducing if that's the mechanism, or if it came from the closed mechanism, it would have been an even weirder system to begin with, or it came from some other method, like local binaries.
I guess just one comment on that, as binaries come in, galactic nuclei, and then eventually get disrupted by the Hills mechanism, they actually undergo something like the Kozai-Lidov effect. So you actually end up with many binaries that are far apart, which end up much tighter than you would have thought. So that enhances the probability of ending up with a tightly bound star like this. Also on the star being a giant, this close to the black hole, there's lots of tidal heating. So it seems more likely that it's some tidally distorted star than that it actually was a giant coming through the Hills mechanism. For the reasons you said, that's pretty tough. So the question I had was, do you have a sense based on, how many galaxies Assassin is sensitive to, what Rubin should be able to see of this kind of event? Because Rubin's cadence is bad for many time domain things, but actually pretty good for this.
Yeah, that's a good question. So I think for the calibration fields, I think the cadence is still set to be 3 days, I think. So I think in the higher cadence calibration fields, we'll definitely have a better chance of observing this. Yeah, I don't know. So has the cadence been set now for Rubin? I thought last time I checked, there was like a question about what the exact
I think there's
strategy.
still, yeah, I was actually wondering also just about, number of galaxies and distance to which you could see this and things like that.
Oh, that's a good question. Yeah, I don't have a number, but again, we're all sky, so south and north. So
Do you have a space density of these objects?
I'll have to get back to you. I don't have, exact number.
I'm curious about the X-ray dimming. So
Yeah.
if you go to the X-ray light, does the uncertainty on the X-ray luminosity decrease when it's dimming? So is this due to some sort of, is there a constant exposure in the XRT observations across all of these? Or are they deep observations when it's dimming?
Oh, so because I've been requesting 2Os, and they've always been consistent. The exposure time hasn't really changed.
Okay, but why is the uncertainty on the X-ray luminosity decreasing when the luminosity is decreasing?
Then maybe I'm misremembering. There was a difference in
Okay,
exposure times.
only because the variation is if you put it on a log scale, I'm not sure how much variation there is. So if it's like exposure time related, then maybe there's something to do with like the background contamination.
I did look at the background, so I know with nicer, you have to be very careful with background, and I do have plots in the latest paper that show it's always well above the background. So definitely not a worry with the background.
But I guess the same thing was seen with the XRT exposure.
Yeah, no, same thing with Swift. Yeah,
Okay.
we did check, make sure.
That's crazy.
Do you need to worry at all about the other AGN? Is it not very? Because these are pretty big.
Yeah, so again, that's always, we have to keep that in mind, right? So, and Chandra is what can spatially resolve. So I submitted another proposal to get more Chandra data, so we can actually very much narrow down the variability between the two nuclei. And we do have some subsequent Chandra, but that is going to be published by an RU student that does show that based on the small number of Chandra data we have, the southern source isn't significantly varying, which kind of gives us hope that it's not being significantly contaminated, but definitely need more Chandra data. And also we don't have any Chandra data during the X-ray severe minimum. So that is future work and we apply for more time.
So when you fit the spectra, do you take that contaminating source into account or not when you're doing these fluxes?
Yeah, no, we separate out, when we extracted the Chandra spectra, we had separate extractions.
For Chandra, yes, but when you're doing the Swift and nicer,
Oh, but it doesn't have the spatial resolution to
yeah, I know, but
separate.
you can add it spectrally, right? You can, so you know what.
Yeah, we should do the subtraction. Yeah, so that is, we're gonna be doing more work for the subtraction using that, yeah.
One question, so you were showing the two test light curves, and it seemed that although they were quite similar, there was some perhaps, qualitative evolution between the shape of the two. So could it be that sort of the timing, the determining of the period evolution has to do with simply some morphological evolution of how the flares look like? If you can comment about that as well.
Yeah, no, I think when we saw that there were these small differences, is this an indication of, stochasticity in the system? That definitely seems to indicate that. I think, again, the goal with the test and seeing that and comparing them is they're not exactly the same. So there's clearly something going on affecting each passage. Which makes sense. Again, it's a messy system. So.
Right. Which is, makes the fact that you're able to measure these, really high quality measurements here so much more remarkable, right?
Yeah, I guess so. It's messy, but very stable.
Yeah.
Brian has something on the chat.
Brian?
No, I was just joking when Elliot or you were commenting on needing a very tight binary, and I was just, before Elliot said that their Kozai would bring them together, I was just saying maybe it's a CV. and then the CVs are also, companions are also inflated. I think Andy King actually relied on this in one of his QPE models as well, so it's not anyways, I was joking, so yeah.
Okay, so if there are no more questions, let's thank Anna once again.